Section: Introduction. In this section, we introduce our work on Segment Anything Model 2, SAM2, which builds upon the foundation model for promptable segmentation in images known as Segment Anything, SAW. We recognize that images are just static snapshots of the real world, while visual segments can move in complex ways. With the rapid increase in multimedia content, especially video data, we see that many important applications in areas like augmented reality, virtual reality, robotics, autonomous vehicles, and video editing require us to go beyond simple image-level segmentation to include temporal localization. We believe that a universal visual segmentation system should work for both images and videos. Video segmentation involves determining the spatial and temporal extent of entities, which introduces unique challenges that are not present in images. For instance, entities can change significantly in appearance due to motion, deformation, occlusion, lighting changes, and other factors. Additionally, videos often have lower quality than images because of issues like camera motion, blur, and lower resolution. Efficiently processing a large number of frames is also a major challenge. While SAW effectively handles segmentation in images, we find that existing video segmentation models and datasets do not provide the same level of capability to segment anything in videos. Therefore, we present SAM2 as a unified model for both video and image segmentation, treating an image as a single-frame video. Our work encompasses a task, a model, and a dataset. We focus on the promptable visual segmentation (PVS) task, which extends image segmentation into the video domain. This task takes input in the form of points, boxes, or masks from any frame of the video to define a segment of interest, for which we aim to predict a spatiotemporal mask, referred to as a masklet. Once we predict a masklet, we can refine it iteratively by providing prompts in additional frames. Our model generates segmentation masks for the object of interest, both in single images and across video frames. SAM2 includes a memory component that retains information about the object and previous interactions, enabling it to produce masklet predictions throughout the video and to adjust these predictions based on the context stored from earlier frames. Our streaming architecture naturally extends SAM to the video domain by processing video frames one at a time and utilizing a memory attention module to reference previous memories of the target object. When we apply this model to images, the memory is empty, and it functions like SAM. To generate training data, we use a data engine that interacts with annotators to annotate new and challenging data. Unlike most existing video segmentation datasets, our data engine is not limited to specific object categories. Instead, it aims to provide training data for segmenting any object with a valid boundary, including parts and subparts. Our data engine, when used with SAM2, is significantly faster, 8.43 times quicker, while maintaining comparable quality to existing model-assisted approaches. Our final Segment Anything video, SAW-V, dataset contains 35.5 million masks across 50.9 thousand videos, which is more than 5 times the number of masks found in any existing video segmentation dataset. The SAW-V dataset presents challenges with small objects and parts that may be occluded and reappear throughout the video. It is also geographically diverse, and our fairness evaluation of SAM2 shows minimal performance differences in video segmentation based on perceived gender, with little variance among the 3 perceived age groups we assessed. Our experiments demonstrate that SAM2 significantly enhances the video segmentation experience. It achieves better segmentation accuracy while requiring 33% fewer interactions than previous methods. Furthermore, SAM2 outperforms earlier work in established video object segmentation benchmarks across various evaluation settings and shows improved performance compared to SAM on image segmentation benchmarks, all while being 63% faster. We have observed that SAM2 is effective across a wide range of video and image distributions, as evidenced by numerous zero-shot benchmarks, including 17 for video segmentation and 37 for single image segmentation. We are excited to release our work under permissive open licenses, including the SAW-V dataset, a version of the SAM2 model, and an interactive online demo. In the following section, we will discuss related work and the various video segmentation datasets that have been proposed to support the video object segmentation task. Early datasets, such as Davis, provided high-quality annotations but were limited in size, making them unsuitable for training deep learning models. YouTube VOS was the first large-scale dataset for video object segmentation, covering 94 object categories across over 4,000 videos. As algorithms improved and benchmark performance began to plateau, researchers sought to increase the difficulty of the video object segmentation task by focusing on challenges like occlusions, long videos, extreme transformations, and diversity in objects and scenes. We find that current video segmentation datasets do not provide enough coverage to achieve the goal of segmenting anything in videos. Their annotations typically focus on entire objects rather than parts, and they often center around specific object classes like people, vehicles, and animals. In contrast, our SAV dataset not only addresses whole objects but also extensively covers object parts and includes significantly more masks than existing datasets. Section Summary. In this section, we introduce the segment Anything Model 2, SAM2, a unified framework for video and image segmentation that addresses the unique challenges of temporal localization in videos, such as motion and occlusion. Our model, equipped with a memory attention module, allows for efficient spatio-temporal segmentation and is supported by the SAV dataset, which contains over 35 million masks across diverse videos, significantly enhancing the capabilities of video segmentation compared to existing datasets and models. Section Task: Promptable Visual Segmentation. In this section, we discuss the Promptable Visual Segmentation (PVS) task, which allows us to provide prompts to the model for any frame in a video. These prompts can be positive or negative clicks, bounding boxes, or masks, and they help us define an object to segment or refine a model's predicted segmentation. To create an interactive experience, when we give a prompt for a specific frame, the model should quickly respond with a valid segmentation mask for that object in that frame. After we provide initial prompts, whether on the same frame or different frames, the model will use these prompts to generate a masklet that represents the target object across the entire video, ensuring that we have the segmentation mask for that object on every frame. We can also add more prompts on any frame to refine the segmentation throughout the video. For our data collection, we utilize SAM2, which we will introduce in the next section. This model helps us build our SAV dataset. We evaluate the model in both online and offline settings by simulating interactive video segmentation scenarios. This includes annotations across multiple frames, following the traditional semi-supervised video object segmentation approach where annotations are limited to the first frame, as well as for image segmentation on the SAW benchmarks. Our model can be viewed as an extension of SAM to handle both video and image data. SAM2 supports various types of prompts, point, box, and mask, on individual frames to define the area of the object we want to segment throughout the video. When processing images, the model operates similarly to SAM. It features a promptable and lightweight mask decoder that takes a frame embedding and any prompts for that frame to produce a segmentation mask. We can iteratively add prompts to refine the masks. Unlike SAM, the frame embedding used by the SAM2 decoder is not directly from an image encoder. Instead, it is influenced by memories of past predictions and prompted frames. This means that the prompted frames can also come from future frames relative to the current one. The memory encoder creates memories based on current predictions, which are stored in a memory bank for use in later frames. The memory attention operation takes the embedding from the image encoder for each frame and conditions it on the memory bank to generate an embedding that is then sent to the mask decoder. We will describe the individual components and training process in more detail below. For training, we jointly train the model on both image and video data. Similar to previous studies, we simulate interactive prompting. We sample sequences of 8 frames and randomly select up to 2 frames to prompt, while also probabilistically receiving corrective clicks based on the ground truth masklet and model predictions during training. The goal is to sequentially and interactively predict the ground truth masklet. The initial prompts can be the ground truth mask with a certain probability, a positive click sampled from the ground truth mask, or a bounding box input, each with specific probabilities. To enable our model to segment anything in video, we developed a data engine to gather a large and diverse video segmentation dataset. We use an interactive model in the loop with human annotators. We do not impose strict semantic constraints on the annotated masklets, focusing instead on both whole objects, like a person, and parts, such as a person's hat. Our data engine went through 3 phases, each defined by the level of assistance provided to the annotators. We will describe each phase in our SAV dataset in detail. In our analysis, we compare the annotation protocol in each phase of the data engine through a controlled experiment. We look at the average annotation time per frame, the average percentage of frames that were manually edited per masklet, and the average number of clicks per clicked frame. For quality evaluation, we define the Phase 1 mask alignment score as the percentage of masks whose intersection over union, IOU, with the corresponding masks in Phase 1 exceeds a certain threshold. We use Phase 1 data as a reference because it has high-quality manual annotations for each frame. We find that Phase 3, which incorporates SAM2, is significantly more efficient and maintains comparable quality. It is over 8 times faster than Phase 1, has the lowest percentage of edited frames and clicks per frame, and results in better alignment. In our performance comparison, we evaluate SAM2 trained on the data collected at the end of each phase while keeping the number of iterations fixed. This allows us to measure the impact of the additional data. We assess performance on our own SAV validation set and on 9 zero-shot benchmarks using a standard accuracy metric, where a higher score indicates better performance, particularly when prompting with 3 clicks on the first frame. We observe consistent improvements as we iteratively include data from each phase, not only on the in-domain SAV validation set but also across the 9 zero-shot benchmarks. Section Summary. In this section, we describe the Promptable Visual Segmentation (PVS) task, which allows users to interactively provide prompts for segmenting objects in video frames, and how our model, SAM2, generalizes this capability by utilizing past predictions and prompts to refine segmentation across the entire video. We also outline our training process, data collection methods, and the efficiency improvements achieved through our interactive annotation approach, demonstrating significant performance gains on both in-domain and zero-shot benchmarks. Section: SAV Dataset. In this section, we present the SAV dataset, which we collected using our data engine. This dataset includes over 50,900 videos and around 642,600 masklets. We compare the composition of the SAV dataset with other common video object segmentation (VOS) datasets, focusing on the number of videos, masklets, and masks. Notably, the number of annotated masks in our dataset is significantly larger than in any existing VOS dataset, providing a valuable resource for future research. We are making the SAV dataset available under a permissive license. Additionally, we utilized licensed video data that we have access to internally to enhance our training set. Our internal dataset consists of approximately 62,900 videos and 69,600 masklets that were annotated in the second and third phases for training purposes. For testing, we have 96 videos and 189 masklets that were annotated in the first phase. Next, we conducted zero-shot experiments to compare our model, SAM2, with previous work on zero-shot video and image tasks. We report the standard accuracy metric for video tasks and the mean intersection over union, MIOU, metric for image tasks. Unless stated otherwise, the results we present follow our default setup, which uses the Hera B+ image encoder at a resolution of 1024, trained on the complete combination of datasets. We then evaluate promptable video segmentation, simulating an interactive user experience. We have 2 evaluation settings: offline evaluation, where we make multiple passes through a video to select frames based on the largest model error, and online evaluation, where we annotate frames in a single pass. These evaluations are performed on 9 densely annotated zero-shot video datasets, using an average of 55 clicks per frame. We establish 2 strong baselines, SAM plus XMEM++ and SAM plus QT, based on advanced models for video object segmentation. We use XMEM++ to generate video segmentation from mask inputs on 1 or more frames, while SAM provides initial masks or refines outputs by using current segmentations as prompts. For the SAM plus QT baseline, we modify QT to accept mask inputs from multiple frames. We report the average accuracy over 56 interacted frames, showing that SAM2 outperforms both SAM plus XMEM++ and SAM plus QT in both evaluation settings. Across all 9 datasets, SAM2 consistently outperforms these methods, demonstrating its ability to generate high-quality video segmentation with fewer interactions. We also assess the semi-supervised video object segmentation setting, where we use click, box, or mask prompts only on the first frame of the video. When using click prompts, we sample either 1, 3, or 5 clicks on the first frame and then track the object based on these clicks. Similar to the interactive setting, we compare our results to XMEM++ and QT, using SAM for click and box prompts, and their default settings for mask prompts. We report the standard accuracy metric, except for the VOST dataset, where we follow its specific protocol. Our results indicate that SAM2 outperforms both baselines across 17 datasets, using various input prompts. This highlights that SAM2 excels in the traditional, non-interactive VOST task with mask input, which the other models are specifically designed for. Finally, we evaluate SAM2 for fairness across different demographic groups. We collect annotations for the people category in the EGO EXO4D dataset, which includes self-reported demographic information from the subjects in the videos. We use the same annotation setup as for the SAV validation and test sets, applying it to 20-second clips from third-person videos. We assess SAM2's performance on this data using 1 click, 3 clicks, and ground truth mask prompts on the first frame. Our comparison shows that SAM2 achieves similar accuracy for segmenting people across gender and age, with minimal discrepancies at 3 clicks and with ground truth mask prompts. However, when we manually inspect one-click predictions, we find that the model often predicts a mask for a part of the person instead of the whole. When we focus on clips where the person is correctly segmented, the accuracy gap for one-click predictions narrows significantly, suggesting that some discrepancies may arise from ambiguity in the prompts. We provide additional details about the model, data, and annotations for the SAV dataset in the appendix. Section Summary. In this section, we present the SAV dataset, which includes 50.9K videos and 642.6K masklets, significantly surpassing existing VOST datasets in annotated masks, and we also describe our internal dataset used for training and testing. We evaluate our model, SAM2, in various video segmentation tasks, demonstrating its superior performance over state-of-the-art methods while also addressing fairness across demographic groups and segmentation accuracy. Section: Image Tasks. In this section, we evaluate SAM2 on the segment anything task using 37 zero-shot datasets, which includes 23 datasets that SAM was previously tested on. We report the 1-click and 5-click mean intersection over union, MIOU, scores in a table, and we also present the average MIOU based on the dataset domain and the model's speed in frames per second, FPS, when running on a single A100 GPU. The first column, labeled SA23 All, indicates the accuracy on the 23 datasets from SAM. We find that SAM2 achieves a higher accuracy of 58.9% MIOU with just 1 click, compared to SAM's 58.1% MIOU with 1 click, all without using any additional data and while being 63% faster. This improvement is mainly due to the smaller yet more effective Hira image encoder used in SAM2. The last row of our results shows that training on our SA1B and a mix of video data can further enhance the average accuracy to 61.4% across the 23 datasets. We also observe significant improvements on the video benchmarks from SA23, as well as on the 14 new video datasets we introduced. Overall, these results highlight SAM2's strong capabilities in both interactive video and image segmentation, a strength that comes from our varied training data, which includes both videos and static images across different visual domains. More detailed results, including a breakdown by dataset, can be found in the specified section. Next, we compare our work to the state-of-the-art in semi-supervised video object segmentation, VOS. While our main focus is on the general interactive PVS task, we also consider the specific semi-supervised VOS setting, where the prompt is a ground truth mask from the first frame, as this has been a common approach historically. We evaluate two versions of SAM2 with different sizes of the image encoder, HERA B+ and HERA L, which offer different trade-offs between speed and accuracy. We measure the frames per second, FPS, on a single A100 GPU using a batch size of 1. SAM2 with the HERA B+ encoder runs at real-time speeds of 43.8 FPS, while the HERA L runs at 30.2 FPS. We present a comparison with existing state-of-the-art methods in a table, reporting accuracy based on standard protocols. SAM2 shows a significant improvement over the best existing methods. We notice that using a larger image encoder leads to notable accuracy gains across the board. We also evaluate existing work on the SAV validation and test sets, which assess performance for open-world segments of any object. Class. In this comparison, we find that most previous methods achieve similar peak accuracy levels. However, the best performance on the SAV validation and test sets from prior work is significantly lower, indicating a gap in the ability to segment anything in videos. Finally, we observe that SAM2 also achieves notable improvements in long-term video object segmentation, as seen in the results from the LVOS benchmark. In the next part, we discuss data and model ablations that informed our design choices for SAM2. We evaluate our MOS development set, which consists of 200 randomly sampled videos from the MOS training split, ensuring these videos were not included in the training data for our ablations, SAV validation, and the average across 9 zero-shot video datasets. For comparison, we report the accuracy under a 3-click input on the first frame, which balances the 1-click scenario and the VOS-style mask prompts. Additionally, we report the average 1-click MIOU on the 23 dataset benchmark used by SAM for the SU task on images. Unless stated otherwise, we conduct our ablations at a resolution of 512 and with a manual subset of SAV and 10% of SAW1B. In our data quality ablation, we experiment with different filtering strategies to enhance quality. We subsample 50,000 masklets from SAV, either randomly or by selecting the masklets that have been most edited by annotators. We find that filtering based on the number of edited frames yields strong performance using just 25% of the data, outperforming random sampling. However, this approach is still less effective than using all 190,000 SAW-V masklets. In the model architecture ablations, we present findings that guided our design decisions, conducted under a smaller model setup with a default input resolution of 512. For each ablation setting, we report segmentation accuracy for video tasks and image tasks, along with the relative video segmentation speed compared to the default setup. We discover that the design choices for image and video components are largely independent, which can be attributed to our modular design and training strategy. Regarding model size, we find that increasing the capacity of the image encoder or the number of memory attention blocks generally leads to better results. Scaling up the image encoder improves both image and video metrics, while increasing memory attention only enhances video metrics. We have chosen to use a B+ image encoder, which strikes a good balance between speed and accuracy. Section Summary. In this section, we evaluate SAM2's performance on the segment anything task across 37 zero-shot datasets, demonstrating that it achieves higher accuracy and faster processing speeds compared to its predecessor, SAM, primarily due to its more effective HERA image encoder. We also explore the impact of data quality and model architecture on performance, revealing that larger image encoders enhance both image and video segmentation metrics, while our modular design allows for independent optimization of image and video components. Section: Relative Positional Encoding. In this section, we explore relative positional encoding. Typically, we utilize absolute positional encoding in both the image encoder and memory attention. In our analysis, we examine different design choices for relative positional encoding. We also assess performance on the LVOSV2 dataset, using 3 clicks on the first frame as a standard for long-term video object segmentation. While the SAM method incorporates relative positional biases, RPB, in all layers of the image encoder, we enhance this approach by eliminating RPB in all layers except for the global attention layers. We adopt a method called absolute win positional encoding, which significantly increases processing speed. We take this a step further by removing all RPB from the image encoder, and we observe no decline in performance on the SAW-23 dataset, with only a slight decrease on video benchmarks, as shown in our results. This change also provides a notable speed improvement at a resolution of 1024. Additionally, we find that using two-dimensional relative positional encoding, 2D ROPE, in memory attention is advantageous. Next, we investigate the effect of cross-attending to object pointer vectors derived from the mask decoder output in other frames. The results indicate that while cross-attending to object pointers does not improve average performance across 9 zero-shot datasets, it significantly enhances performance on the SAV validation dataset and the challenging LVOSV2 benchmark. Therefore, we decide to consistently use cross-attending to object pointers in conjunction with the memory bank.